Hey guys, so this is my second video on L'Hopital's rule, and in this one we're going to be talking about the indeterminate forms with infinity. So this is the second video in this lesson series. So just to give you a quick overview, in the first video I talked about all these different indeterminate forms, and I really just focused on this first form so that I could introduce the idea of L'Hopital's rule. So I'm assuming that you understand that now, and I'm going to focus on these forms in this video, and then in the third video I'll focus on these two forms, and these are kind of like a different process, so that's why they're getting their own video. So just a heads up, so this form here, I think that this first form is pretty straightforward. These other two forms, these are going to require a little bit of cleverness, so we're going to build up to it. So L'Hopital's rule says suppose f and g are differentiable on an open interval containing the point a, and f of a equals g of a equals 0, and g prime of x equals 0 if x does not equal a. So if all these conditions hold, we got L'Hopital's rule, which basically said then if you were getting this 0 over 0 form, so if this was 0 and this was 0 as when you have the limit as x approaches a, to deal with that you can just take the derivative of the top and the bottom and then take the limit. So that's what L'Hopital's rule was getting at. So there's an extension of this actually. L'Hopital's rule also works in the same way if we get infinity over infinity. So if I basically get that this is infinity and this is infinity as x goes to a, or x goes to infinity, by the way, like whatever happens as you're taking the limit, if this is infinity over infinity, you can really do the same thing of taking the derivative of on the top and on the bottom. So I want to show you just a couple of examples of that, and then we'll build up to the other indeterminate forms. So for this first limit, I have the limit as x approaches pi over 2 of secant x over 1 plus tangent x. And so the thing is, if you were to try to plug in pi over 2, what would end up happening is you would get this infinity over infinity form. And so that's what tells you can use L'Hopital's rule. So I can really then just take the derivative of the top, which is going to be secant x tangent x, and then the derivative of the bottom, which will be secant squared x. And now you can see that there's some simplification that can be done. And notice I continue to write the limit notation because that's proper. And so then this will simplify to tangent x over secant of x. And then, you might want to just think about what is tangent. So tangent is sine of x over cosine of x. And then, so secant x, so just maybe I'll write that over to the side. So we know that secant x is equal to 1 over cosine of x. Therefore, the fact that the secant is in the bottom, I can really rewrite it then as times cosine of x over 1. So the two cosines cancel out. That's what I'm getting at there. And then let's see. So this is just going to leave me with really sine of x. And so that's all I've got to figure out then. And so I can just plug sine of pi over 2 into this. So that just equals 1. So there's our answer. So that's how you're going to use L'Hopital's rule. Okay, so let's take a look at another example here. So here's another example. Now notice in this case, I've actually got x going to infinity. And so in this case, I get that infinity over infinity type thing. So that tells me to use L'Hopital's rule. So notice now what happens when I do this. So I continue to write the limit notation. The derivative of the top is e to the x. The derivative of the bottom is going to be 3x squared. Now, I talked about in the first video that you always want to check that you are still getting this indeterminate form. So if I try to evaluate the limit as x goes to infinity, I still get infinity over infinity. My infinities look terrible today for some reason. Okay, so I'm going to take another derivative. So this will be e to the x over 6x, and we still have the same problem, right? So, okay, keep taking the derivative. Okay, so now I'm going to have e to the x over 6. Okay, now in this case, we do actually get something that's not infinity over infinity. So I just want to compare this for a moment. Notice this was infinity over infinity. This was infinity over infinity. This was still infinity over infinity. This is what happens every time I try to take the limit. But now in this last case, if I try to evaluate this, well, now what's going to happen is I'm going to have, let me break this into two limits actually, so I've got the limit as x approaches infinity of e to the x, and then I've got the limit as x approaches infinity of 6. So I just want to make this kind of nice and clear what's happening. So the top in this case now, this is going to infinity, but the bottom here, this is going to just 6. Now, we don't want to do calculations with infinity because that's kind of like a no-no in math. Like infinity is not a number, so you can't do calculations with it. So you don't want to write like as a formal answer infinity over 6 because probably most math teachers are going to get kind of annoyed by that because again, we just can't do traditional calculations with infinity. So you can kind of split up your analysis like this and then say, well, infinity over 6, the 6 really isn't going to do anything when you've got infinity as part of this. So the whole result here then is just going to equal infinity, and that's it. So that's actually the answer in this case. But notice the reason it's infinity is because we did all of this other analysis. It's not just, oh, I got infinity over infinity, therefore it equals infinity. It's something a little bit deeper, and so you just want to kind of stay cognitive of that. Okay, so now I want to pivot and I want to show you some of the other forms and how do we deal with them. So the first thing I just want to notice here, so I've got the limit as x approaches infinity of x times sine of 1 over x. So if you think about this, so x as x goes to infinity, this is going to go to infinity. And then this sine of 1 over x as x goes to infinity, this is really going to give you sine of 0, which equals 0. So notice what really ends up happening here is we get this infinity times 0 form. This is not to say that we're doing a calculation with this, but this is just to kind of point out like this matches kind of that indeterminate form that we're trying to sniff out here. Okay, so when this happens, what do you do? So you can't use L'Hopital's rule quite as like straightforwardly. It's not like, oh, I just take the derivative and I'm good to go. But what you can do with this is you can make a clever manipulation to force L'Hopital's rule to apply. So let me just show you what the manipulation would be, and then we'll kind of reflect on why this works. So, all right, I don't want this form. Instead, what I want to have is I'm going to declare a new variable, h. H is going to equal 1 over x, which would then make 1 over x, which would then make x equal 1 over h. So here's a substitution that I want to make. So I want to change up how I think about this. So notice what happens when I do this. X becomes 1 over h, and sine of 1 over x will become sine of h. Okay, now in doing this, I also have to change the limit. So notice I haven't written that down yet. So this will no longer really serve me if I leave the limit like this, because if I just rewrite this and just change, x to h, I'm still going to get 0 times infinity. But what I can do, and also that kind of actually changes the problem, right? Because this here should be going to infinity. This x here should be going to infinity. And this sine of 1 over x, this should be going to 0. So if I just try to change this to h to infinity, so just to kind of play this out for you. So if I tried to change this to h to infinity, notice now this 1 over h goes to 0, and this sine of h goes to infinity. So I've actually kind of flip-flopped the two values. So it would be wrong to make this particular adjustment. So instead, I still want to have a limit, but I want to have a limit and I want to adjust it so that I still get this first value here will still end up going to infinity, just like it did before. So the way to then equivalently kind of flip-flop this limit would be to change this so that h goes to 0 on the right. And so now if you think about that, so this will still go to sine of 0, and this will still go to infinity. So you have to think about what happens just in general if you have like the limit as x approaches 0 on the right of 1 over x. This is just equal to positive infinity. You can look at a graph just to confirm that if you want. This is like old limit knowledge here, so I'm going to kind of just gloss over that a little bit. Okay, so now I have this limit is really equivalent to this limit, but this actually gives me some better leverage because look at what happens. Now I can rewrite this particular limit to look like this. So I've got the limit as h approaches 0. This is going to be sine of h over h. So I just multiplied them together. And this is still 0, goes to the right. But now, in this case, what I'm going to end up getting is something that I can work with. I've like just by making this little manipulation and now thinking about this. So we know what this looks like really in terms of the limit, but now if I flip it to this and I just think about the act of plugging 0 in for h, so notice how this kind of changes the way that we think about this. Sine of 0 is 0, and h equals 0 is just going to give me 0. So now actually I've turned this into 0 over 0 form in just being kind of clever in how I manipulate all of this. Neat, huh? So now I can use L'Hopital's rule. So I can go ahead and take the derivative of the top, which is going to be cosine of h, and then the derivative of the bottom is going to be 1. So now I can just take really cosine of 0, which is just going to equal 1. And so now I'm done. And so you'll learn kind of how to apply these sorts of tricks as you go through problems. So at first you might think, oh, I would have never thought of that. And that's okay, actually. That's like why you're in class, right? So that you can learn how to be clever and what kinds of tricks you can use. So this is kind of one of the standard tricks that we use with these types of problems. Okay. So now I want to take a look at another problem like this. And I run into a similar issue. So notice that this square root of x, I've got the limit as x approaches 0 on the right of the square root of x times the natural log of x. So this is going to go to 0, this square root is going to go to 0, and then this natural log of x is going to go to infinity. So we have that same problem again. So now I want to show you the other trick that we can use to manipulate this, because it's not like now I can make that choice of, h and kind of cleverly flip-flop these two x's. So if that first trick doesn't work, the other way that you can do this is you can manipulate kind of the freestanding term or a freestanding term into a fraction. So the square root of x is the same thing as 1 over the square root of x. So take a second to prove that to yourself. If I actually try to write out this little division problem here, this would be 1 divided by 1 over the square root of x. And then when you divide by something, you're really multiplying by the reciprocal. So this would be 1 times the square root of x. So this does indeed just equal the square root of x. So I'm going to make this kind of funny manipulation here. But let's see what that buys us. Let's see if that gets us something. And by the way, this is like kind of a standard practice. So sometimes you have to play around with these. It's not like I can just tell you, oh, just do this and it's going to work. You're getting to the point now in calculus where you have to play around a little bit more. Okay, so I have just changed the problem to look like this, but now let's think about what do we get. So I know that as 0 goes to, or as we go to 0 on the right for the natural log of x, this limit on top, this will still go to infinity. And now this limit in bottom is also actually going to go to infinity. So I've made just a slightly different way of thinking about this problem, but now I've got infinity over infinity. And once I hit that format, I found a way to cleverly manipulate this. I can use L'Hopital's rule. So now I can take the derivative of the top, so that's going to be 1 over x. And then I can take the derivative of the bottom, and the derivative of the bottom now in how I've written this. So remember, just to like make this even more clear. So going just to this form here, if I wanted to think of this as one other way to do this, this would be x to the negative 1/2. That would be another way to write this. So I'm taking really the derivative of x to the negative 1/2. So when I do that, I get negative 1/2 x to the negative 3/2. So there is kind of my whole little manipulation here. But now that I've written all of this out, I can move towards simplifying this. So now we've got to kind of clean up the mess that we've made, if you will. So I've got, really, this is 1 over x. Here's the numerator. And then this is going to be times negative 2x to the 3/2, to the positive 3/2. So I can bring all of this up to the numerator. And from here, now I can manipulate this a little bit more. So this is going to be, let's see, I better write it up here. The limit as x approaches 0 on the right. So now I've got negative 2x to the 3/2 over x. So this is going to equal the limit as x approaches 0 on the right of negative 2x, well, really just to the 1/2. And so now this is a limit that I can evaluate. This is just going to be -2 times 0. So the whole limit will just equal 0. And so that's it for that one. So that's one set of tricks that you can try. And I want to show you the other tricks. And just by the way, I have more example videos on these types of concepts if that's something that you're looking for. So I'm just kind of introducing it here. And if you want to see more, I've got more example videos. Okay, so now let's talk about kind of the last indeterminate form that I'd mentioned. So that infinity minus infinity. So how do you know that you've run into this? Well, notice now I've got the limit as x approaches infinity of this natural log of 2x minus the natural log of x plus 2. Okay, so this guy is going to go to infinity, and this guy is also going to go to infinity. So just notice kind of the format here is this infinity minus infinity form. So we are good to go. But now we're going to have to talk about how do you manipulate this so that you can actually use L'Hopital's rule. So in this particular case, the context is going to matter. The context always matters with L'Hopital's rule type problems, by the way. So in this case, I have logs here, natural logs, and I've got a subtraction problem. So that actually is a logarithmic property. And so this actually is a division problem in disguise. So using properties of logs, and so that's like what you can look up if you are rusty on them, is just Google property of logs if you want to see a quick list. So if I use properties of logs, this would be actually how I could rewrite the problem. Top minus the top minus the bottom is really, this is going to be the top part, this will be the bottom part. Okay, and so now notice what really ends up happening. I've almost got this in L'Hopital's form, or in that form that I want for L'Hopital's rule. The only issue is I've got this natural log here. So now we have to think about what we know about limits. And if you think about limit properties, this natural log is not really going to do a lot in the context of this particular problem. So, you know, if this is going to infinity, this natural log is going to infinity. So what I'm saying is we can kind of move the natural log to the outside so that this becomes the natural log of the limit as x approaches infinity of 2x over x plus 2. And so now look at how clever this is, because now I get something that becomes infinity over infinity. And that's what I need to take L'Hopital's rule. So now I've got this natural log hanging out here, but now I can take the derivative of the top, and I keep writing the limit notation. The derivative of the top is 2. The derivative of the bottom is just going to be 1. And so lo and behold, now we're really good to go. So this is just going to end up becoming the natural log of 2, and that would be your answer in this case. So that's it. So that's one way that you can kind of manipulate the problem, but let's look at a slightly different way. So now I've got the limit as x approaches 0 of 2x plus 1 over 0 minus 1 over sine of x. And this actually has that same thing. So this is going to involve this infinity over infinity type form. But in this problem, we don't have natural logs. So it's almost like having that natural log made it a little bit easier on us because we could just leverage the properties. Here we cannot be so clever. But what we do have are two fractions, and so if I just want to think differently about my fractions here, I could just get a common denominator. And so that's exactly where I want to start. I want to rewrite these so that they're all under the same denominator. So what I'm going to do, I've got this 2x plus 1 over x, so I'm going to multiply this by sine of x over sine of x. And then for this one, I'm going to multiply this by x over x. And so let's just sort all those details out and let's see what that buys us. Maybe that will help us. So now I've got 2x plus 1 times sine of x minus x, and then all of this will be over the denominator x times sine of x. Okay, so I want to encourage you not to go into computer mode. Sometimes people write this out and then I notice that they'll go, oh, signs cancel out. No, you don't want to do that. That was the whole point of this, was to get this all together on the same area. So do not go canceling this out. So now if I plug in my 0 here, so notice how this actually does change the context of the problem. By plugging the 0 in, So I have this whole thing, which is going to be 1 times sine of 0, which is 0 minus 0. So the top here is going to be 0. And then the bottom, this is going to be 0 times 0 if I just plug in 0. So I've actually now got the conditions I need for L'Hopital's rule. Awesome. So now you just have to take the derivative. And granted, that's going to take a little bit of work in this context, but it's not the end of the world. So with this part here, I'm going to have to use the product rule. So this will come out to 2 sine x plus 2x plus 1 times cosine of x, and then minus 1. And then in the denominator, I have to use the product rule again. So this will just become sine x plus x cosine of x. Now, I could simplify and go through all that, but I'm actually just going to see if just plugging in 0 is going to work now, if I can just go that route. So let's see, if I plug in 0, so this is going to be 0 plus 1 minus 1 over 0 plus 0 times 1. And so what does that give me? That just gives me, 0 over 0. Okay, so that's okay, right? We can totally deal with that. So let me clear some space, and basically that just means now we've got to take another derivative. Oh well, so let me clear some space. And let's take the derivative of the top and bottom again and see if that helps us at all. Okay, so now taking the derivative of the top, this is going to become 2 cosine x. Now I got to take the product rule here, so this will be, I guess this will really be minus, let's see, plus 2 cosine x minus 2x plus 1 sine x, and then the derivative of this 1 is just going to drop out, so there's the derivative of the top. Now working on the bottom, this will be cosine of x plus cosine of x minus x sine of x. Okay, so now we do the same process again. I'm not even going to try cleaning up the derivative in this case. I'm just going to see if plugging in 0 is going to work. So let's see, if I plug in 0, I'm going to get 2 times 1 plus 2 times 1, really minus 0, over 1 plus 1 minus 0. And so what does that give me? So that gives me 2 plus 2 over 2. And so that will ultimately equal 4 over 2, which is 2. And so, hey, now we actually got the answer that we wanted, or something that wasn't 0 over 0, I guess. So we evaluated the limit, and we found the answer. And so, yeah, there are going to be more example videos on this if you're looking for more, but you do have to kind of play around with this. It's not always going to be immediately obvious, so you have to have some patience and be willing to try more than one thing. And be willing to think through what are some other ways that you can kind of go about this. The way that you kind of learn with this kind of thing is really practice, 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 and you will just kind of start to get a sense of the tricks. So it just takes some time. So try not to get frustrated. Okay, guys, thanks for watching. I'll catch you next time.